Hello, welcome back to Mech 416/816 Engineering Acoustics. In this video, we are going to start our chapter 4, which focuses on reflection and transmission. This is chapter 6 in the book, and we're going to start by talking about changes in media. So when an acoustic wave traveling in one fluid or one medium encounters a boundary of another fluid, so you can think of changing from oil to water, or water to oil, or water to air, these kinds of boundaries. There is an interaction that is generated at that boundary, which causes part of the wave to be reflected and part of the wave to transmit into the other media. To simplify our discussion, we are going to assume the following. First, one, that both the incident wave, that's the wave that is traveling through the first medium towards the boundary, both the incident wave and the boundary between the media are planar. So the boundary between the media and the incident wave are both going to be planar. Meaning that there's no rotation. Also meaning that the boundary itself is a plane. 2, we're going to assume that all of the media are fluids. So we're going to not consider any kind of fluid structure interaction or how acoustic waves are influenced by some kind of boundary. So again, all media here are fluids. Okay, so what we're really going to be interested in are the ratios of the pressure amplitudes of the reflected waves with respect to the incident wave, and then also the transmitted wave with respect to the incident wave. And these are going to depend on the characteristic acoustic impedances, the speeds of sound of the two media, and then the angle of that incident wave. Now, in this class, we're only going to consider normal incidents, but you can study oblique incidents, and some really interesting things pop up. If you're interested, I suggest you go through the book and read that to find out more. All right, so we're going to say that let the characteristic acoustic impedance of the fluid that the incident and reflected waves travel in be R1, which is then equal to rho 1 and C1. So this is the density and speed of sound in the first fluid, and then R1 is the characteristic acoustic impedance in that first fluid. And rho 1 here is an equilibrium density. Then R2 equal to rho 2 times C2 is going to be the second fluid, which is where the transmitted waves propagate in. We're going to let Pi, PR, and PT be the complex pressure amplitudes of the incident, reflected, and transmitted waves respectively. Then we can define transmission and reflection coefficients as T over bar equal to the amplitude of the transmitted wave, PT, divided by the amplitude of the incident wave, Pi. And for the reflected wave, we'll have R over bar being equal to PR over bar divided by Pi over bar. So since the intensity of a harmonic plane wave is defined as P squared divided by 2R, we can then also compute intensity, transmission, and reflection coefficients, and these will be real, and they are given as Ti is equal to the intensity of the transmitted wave divided by the intensity of the incident wave, which is then equal to R1 over R2 times the absolute value or the magnitude of the transmission coefficient squared. And then for the reflected intensity, we get Ri is equal to IR over I, which in this case is equal to the magnitude of that reflection coefficient squared. Okay, in the next video, we're going to go through and study transmission from one fluid to another.